And we have, again, with functions, again, a function is a mathematical relation where if you have an xy coordinate system, it's going to follow that for each x value, which is going to be the independent or input variable, there's going to be only one and only one corresponding y value. And the y value is going to be the inputs, I should say the output or dependent variable. Okay, so for each x value, for each input, there's only one corresponding output, and that is where the relation becomes a function. And again, we looked at samples of whether we have, say, this each set of ordered pairs is going to be a function or not. And again, if the x values throughout do not repeat with different y values, then the relation is going to be a function. And again, we have D for domain. Okay, domain will be the set of x values in the mix, and the range that I have labeled as R, that's going to be the set of y values. Okay, so domain is for what we have in x, or the input, and the range is going to be what we have in y, or the output. And again, just like the second sample here, with these four ordered pairs, we have 3, 4, and 3, 10. And again, we have a repeating x value, and the repetition happens to be with a different y value. But again, for each x, there's only one corresponding y, and that is the reason this second case is not a function. And again, so now there could be a case or situation where you could have the point to repeat, and if the x value repeats, but it's still with the same y value, okay, then you're going to have the relation to still exist as a function. And we'll be looking into further cases about the features of a function. And so we're going to make a bit of a transition from ordered pairs to graphing. And graphing is sort of expanding the model of what the ordered pair sets were illustrating. And in the case of graphing, okay, for a function, okay, we're going to have there's some features here. So we have in graphing, a function is going to satisfy what is referred to as the vertical line test. Okay, there's going to be another test like the horizontal line test, but that's going to be for subcategory of the that we have within the family of functions. Okay, so we have in graphing, okay, a function is going to satisfy the vertical line test. Okay, and with the vertical line test, okay, you're going to have a vertical line will intersect the graph of a function at most one point. For all x values. This might seem a bit wordy, but a vertical line will intersect the graph of a function, say by at most one point for all x values. and I'll give you some examples as well as examples of non-functions. And so if you were to test out with using the vertical line test, and we'll say that we have starting out, so we have with the XY coordinate system. Now I'm not going to assign numbers, but again, you have the x-axis and the y-axis will be number lines. X runs horizontally, the y-axis runs vertically. And we'll say that we have a function or non-function, okay, and we can say we have y is equal to f of x, and I'll get into the f of x details in a moment, but you're looking at y is equal to 2x plus 4. And with the vertical line test, if I put in a vertical line and I run it through the graph, okay, so you have running from end to end, from left to right. Okay, notice you have at each stage you have the intersection at most 1 point. So there's no x value where you're going to have the vertical line and the graph of y is equal to 2x plus 4 to meet at 2 or more points. So you have at most 1 point. So this is going to be a case of what we have with a function. And let's say that if we have and let me adjust the view here. Okay. Say we have a graph. In fact, not just one graph, I just want to have sort of like portions, like pieces of a graph. Okay, so I have this part. So I have this portion, and I'll just let's see. I'm gonna leave that out. Okay, you don't have an expression that defines what we have up here. Okay, but if you were to run a vertical line, okay, so just kind of going from end to end. So you don't have any point of intersection yet. And once you get to this first line segment section, you have along each x value have meeting at 1 point, and then there's a bit of a gap, so you have no point of intersection. Then we have this horizontal bar, so you have again the intersection at most 1 point, and then there's a gap, and again just going through each section you have the intersection at most 1 point. So this particular portion, that is going to be a function. And if you have like separation or degrees of separation between the links, you might have what would be referred to as a piecewise defined function, and that's going to be a future topic in itself. Now let's say that if we have as a case and we'll say that we have say we have a circle, and we'll say that with we're going to have this one to be defined by the equation. Okay, so you have x squared plus y squared is equal to 4. And this is going to be a case of a circle that is going to be centered at the origin, and that will have a radius of 2. Okay, and circle does have its properties. Now, in terms of taking what we have with the vertical line, okay, say if we move this from left to right, okay, once you get to negative 2, 0, this edge point, notice we start to move in the least bit out to the right. Guess what? We have for the same x value, you got a couple of points of intersection here. And again, to satisfy the vertical line test, a vertical line will intersect the graph of a function at most 1 point for all x values. And because of this particular predicament, okay, so you have 2 points of intersection. Now, full circle does serve its purposes, but a circle is not a function. Okay, and you might be looking at, okay, notice you have the upper half of a circle and the bottom half of a circle on the same at the same location x, okay, and we have resulting 2 points of intersection. And you might have posed a question now: can you take half a circle? In other words, can a semicircle be a function? And in this particular case, all right, we have to have a semicircle, and we'll take like maybe the upper half. Again, just the topic of circles is kind of like in the realm of Math 172, but just looking at the features of circles and semicircles, like through the lens of the vertical line test and whether we have the graph to represent a function. Okay, say we have for this one. Okay, this would be a case where we had that y is equal to the square root of 4 minus x squared. So you have y is equal to the square root of, and this one, so you have y is equal to the square root of 4 minus x squared. And if I run a vertical line through this, so you have at most, even going from end to end, you will have the intersection at most 1 point. Okay, so a semicircle can be a function. And going back to the question, I just want to highlight this as well. So if we did like so you have 0, -2, 0, 2, 2, 0. After this portion, one notation would be like where we have the x is, we'll say that in this one, so you have like with this particular semicircle, say if I have that x is equal to the square root of 4 minus y squared. So you're looking at just the right half of the circle that we had originally that turned out to not be a function. So we have, and if I were to insert a vertical line, so a semicircle of this type, and we have, again, 2 points of intersection at the same x value. And because of this, because of there being 2 points of intersection between the vertical line and this particular semicircle, now that which represents x equals the square root of 4 minus y squared, or x equals the square root of 4 minus y squared, that is not going to be a function. But again, what I had earlier with the upper half, we have that was a function because you had at most 1 point of intersection. So so in terms of, can a semicircle be a function? Yes. But depends on the layout. It's like if you have upper half, lower half, it is going to be a function. But if you're looking at the right half or the left half, it is not going to be a function because right and left halves would violate the vertical line test. And just another case here. Let's go back to the second illustration. And it's kind of going back Okay, so you had these three line segments. Okay, we said that that was a function. And let's say that if I sort of include a little something here, so you have another horizontal line segment. And I ran a vertical line through this. Guess what? Okay, for each x value, there should be at most one point of intersection between the vertical line and that which we're attempting to represent as a function. And guess what? With this particular part here, same x value, 2 points of intersection. So you have in this layout, okay, this one is not a function. Okay, and again, just for what we have with functions, again, for each x value, there should be one and only one corresponding y value. Okay, and so anytime you see two or more points of intersection, it kind of goes back to one attempt that the sets of order pairs are trying to illustrate. Okay, so again, graphing, vertical line test. Again, for there to be a function for each x value, there should be one and only one corresponding y value. And if there are two, like over here, or again with the circle, okay, you're not going to have a function. Okay, whereas with like 2x plus 4, as well as the upper half of the circle right here, for each x value, there's only one corresponding y value. Again, those are illustrations of functions. Right, and now in what we have regarding functions, okay, now we're going to cross over to some of the notations, and I had put up from the start the f of x notation. And for what we have regarding functional notation, okay, so we have with functional notation, again, we had y is equal to f of x. Now, it's not limited to just the letter f. It could be g of x, h of x, z of x. But f of x is the most common notation. And again, we have with x, okay, that's the input or independent variable. And whatever we put in for x is going to affect the outcome. In this case, we have y. Again, that is the output or the dependent variable. Okay. And just in the crossover, okay, where we have like y is dependent upon x. Okay, we have for functional values and expressions. Now let's say that if we have given a function, and we'll let this one be y is equal to f of x is equal to x squared minus 3x, and on the basis of the function that is given, say if we were to determine, let's say, f of negative 3, f of 1, as well as f of x of 2. Okay. So we got here. Okay, so again, f of x, this is just the functional notation for what we normally say is y. Okay, so we have with our function. Okay, so you have f of x, again, f of the input is equal to the square of the input minus 3 times the input. Okay, so take what's in parentheses. Again, I'm going to square what's in parentheses minus 3 times that which is in parentheses. And if I shift over, going from x to negative 3, so if I replace x with negative 3, I'm still going to perform the same types of operations. So on the other side, I'm going to have, just as I squared x, I'm going to square out to negative 3. And then I have subtraction of 3 times x. This will translate to the subtraction of 3 times negative 3. So for the square of negative 3, or negative 3 times negative 3, that will be a positive 9. Negative 3 times negative 3 is another positive 9, and we have 9 plus 9, which is going to be 18. And so what this is saying essentially is that whenever x is equal to negative 3, y turns out to be 18, and say for y is equal to x squared minus 3x, a one point among infinitely many others that will be on the graph of y is equal to x squared minus 3x is going to be negative 3, 18. And say if I have f of 1. Okay, so replacing x with 1, so I have 1 squared minus 3 times 1. So we have 1 squared is 1, negative 3 times 1 is negative 3. 1 minus 3 comes out to negative 2. Again, for the specified inputs, okay, when x is negative 3, y is 18. When x is 1, okay, y turned out to be negative 2. Okay, so you have 1, negative 2. So those are, okay, negative 3, 18, and now 1, negative 2. Those are going to be 2 points among infinitely many others. They'll be on the graph of y is equal to x squared minus 3x. Now, going from a functional value to a functional expression, and if I change the variable input of x to the variable expression x plus 2, and if I have the same kind of follow through, so just as I squared x, I'm going to square all of x plus 2. Then we have with minus 3x, minus 3 times that which represents the input, and we'll have minus 3 times all of x plus 2. Again, just this might seem like a little redundancy, okay, but again, for the square of x plus 2, just a reminder, easy part to remember is to square out x as well as 2, but remember the square of x plus 2 translates to x plus 2 times x plus 2 when writing in terms of multiplication. So again, we have x squared. Outside, inside products will each be at 2x. So 2x plus 2x is 4x. And the last product, again, we have at 4. So we have in following through for the square of x plus 2, we're going to have x squared plus 4x plus 4, and then distributing negative 3 over the quantity of x plus 2, we have minus 3x minus 6. And so we have x squared. Now we have 4x minus 3x, so this will leave us with x. And 4 minus 6, okay, that is going to leave us with negative 2. And that will be the resulting functional expression whenever the input is adjusted from x to x plus 2. All right. And tell you what, just for the next few moments, okay, let's say we have given a function. Now we say have given f of x is equal to 2x squared minus 3x plus 7 and let's see what we get for f of negative 3 once again, f of 5, and for variable expressions, let's see what we get for f of x plus 1, and we'll discuss in a few moments. Okay, for this function, okay, we have, again, you have representing y, you have f of x, which we have set equal to 2x squared minus 3x plus 7. And if I'm looking for specific points, okay, and the first of which we're looking at determining just what the y value is going to be whenever x is set to negative 3. So in terms of what to do with negative 3, okay, so I have that to represent x for this function. So for 2x squared, then we have 2 times the square of negative 3 minus 3 times x, we have minus 3 times negative 3. And we have followed by the addition of 7. Okay, so for the square of negative 3, okay, square of a negative is going to be a positive. So this will be 2 times 9. And then we have negative 3 times negative 3. Okay, so this will be a positive 9. And we have followed by the addition of 7. And in the follow through case, so we have 2 times 9, which is going to be 18. And then we have 18 plus 9, which is going to be 27. And then we have 27 plus 7, which is going to be 34. Okay, so whenever x is negative 3, y is 34. So negative 3 and 34 would be a point on the graph of this particular function. Now for f of 5, here we have 2 times the square of 5 minus 3 times 5 followed by the addition of 7. Okay, so you have 5 squared is 25. So we're going to have 2 times 25. Negative 3 times 5 becomes negative 15. Again, we have plus 7 to tag along. Now we have 2 times 25 is 50. We have 50 minus 15 is going to be 35. And then we have 35 plus 7 comes out to 42. So 542 would be another point on the graph of the same function. And for what we have in the case of f of x plus 1, so for 2x squared, and we have this time 2 times the square of x plus 1. And I have minus 3 times all of x plus 1. And we have followed by the addition of 7. And we have in the follow through. So we have for the square of x plus 1, okay, this will be x squared plus 2x plus 1 and for negative 3 over the quantity of x plus 1, I can remove the parentheses at this particular stage. So we have negative 3x minus 3 followed by the addition of 7. And I'll just work down here. Okay, so distributing 2. So we have the resulting trinomial. We have 2x squared plus 4x plus 2. Okay, then we have the subsequent terms. We have negative 3x minus 3 plus 7. I can go ahead and cluster these together where we have plus 4. And then just combining all like terms together. So we have 2x squared is the only squared term in x. First order in x, we have the terms 4x and negative 3x, so they will combine to positive x. And then we have 2 and 4, and that is going to make 6. So for the variable input, x plus 1, and operating in accordance with the given function, we have the output to end up as the trinomial 2x squared plus x plus 6. Okay. Now the other day, I believe it, I said whenever we looked into functions, especially ordered pairs, and that the x value set would make up what constitutes the domain. I said that you'll be looking at domain time and again. And for what we have in the case of domain, okay, just not only as a set of x values, but also just looking at some of the potential restrictions regarding the function itself. And now for the domain of a function, okay, and for this part, we'll be looking at interval notation quite a bit, kind of like some of the absolute value scenarios we drew up, especially with the inequalities. Now, for what we have in the case of what we have for the domain of a function, okay, now for the domain of a function, y is equal to f of x. Okay, this is going to be the set of all values x. So the set of all values of x, okay, such that the function itself is defined in the set of all real numbers. Okay, and you probably have heard the phrase several times over, keeping it real. Well, in the case of domain, your values of x serve the purpose of keeping the function defined in the set of all real numbers. And just kind of give you a visual. Let's say that if you're looking at determining the domain, so if we're looking at determining the domain, expressing the results in interval notation. And we'll say we have as a leadoff function. Okay, we can say that we have y is equal to f of x is equal to, we'll say, 3x plus 7. Okay, now, it's like section R6, I believe it was. We're dealing with complex numbers, and it's like from here on out, okay, we're not dealing with the complex numbers. So you will not see them in test 2 or test 3 or the last example, which will be test number 4. So the complex numbers are relegated to the past. All right, so for y is equal to 3x plus 7. Okay, now in this one, we do not have a fraction. We do not have an even root radical. For y is equal to f of x equals 3x plus 7. So there's nothing that keeps x from being 0 or from being a positive or even a negative. So in this particular case, there are no restrictions on x. So there will be no restricted values. And what this means is that for the domain, okay, that is going to be the set of all real numbers. And the interval notation for this, again, will be parentheses around negative and positive infinity. And let's say if I have a function, f of x is equal to, let's say we have 2x squared minus 4x minus 19. Again, we have a bit of history to repeat. Okay, we don't have any fraction, we don't have any radical. So we have history to repeat. Okay, so you have no restrictions on x. So I have, once again, the domain is going to be the set of all real numbers. All right. Now, let's say that if we have a fraction this time around, and say we have a function, and say we're going to have equal to 3x plus 4. And we have all over x minus 5. Okay, this time we have a fraction. And again, for a fraction to be defined, okay, now the bottom value cannot be 0. So this time we're going to have a restriction. And this is going to be the x minus 5. Cannot be equal to 0. Okay, so we're going to have, in effect, we're going to have x cannot be equal to 5. And just, okay, now we're going to be looking at expressing the solution in interval terms, but just to kind of give you the setup in terms of how the dynamics will be carried out. So we have 5 to be the focal point, and if you notice, 5 is not included, so we have a hole in the graph, and we're going to have from here, let me do something right quickly. Yeah, I'll just change the color. Okay, so we're excluding 5, but everything else greater than as well as less than will be in the mix. Okay, so 5 is excluded. Now for the domain of this particular rational function, reading in order from left to right. Okay, so again, you have going from negative infinity Again, infinities are balanced, so parentheses only go around negative and positive infinity. And we have approaching, but not including 5. So you have a parenthesis. So this is for the left half here, set of values x less than 5. And then we have uniting with, and with excluding 5, you're going to have those values of x greater than 5. So you have going past 5 and heading on out to infinity. So that would be the domain in interval notation for this particular function. Okay. Now, let's say that if I have f of x is equal to, let's say you have x squared minus 21 all over x squared minus 16. Okay. And again, just for the restrictions. Okay. Again, you can have a zero numerator in a fraction as long as you do not have a zero denominator. So the restriction comes from x squared minus 16. Again, x squared minus 16 cannot be zeroed. And if that is the case, then the factors of x squared minus 16 cannot be zero in value either. So here we have x plus 4 cannot be 0, signaling that x cannot be negative 4. And with x minus 4, this cannot be 0, so x cannot be equal to 4 either. Okay, so both negative and positive 4 are going to be left out. Everything else before, after, and in between will be included. Okay, so for what we have, again, working in the determination of the domain, utilizing interval notation. Okay, so you're going to have, notice thanks to the negative and positive 4 exclusions thereof, okay, we're going to have 3 sections that will make up the interval notation. So you have those values x that will be less than negative 4. So you have from negative infinity, approaching but not including negative 4. And then we have going past negative 4, approaching but not including 4. And then for the rest of the set, you have those values of x that will be greater than 4. Okay, so if you notice, okay, we had 3 sections, whereas what we had before, we had 2 sections. And basically what happens is that the more exclusions there are, you're going to have more subintervals formed in the interval notation that represents the domain. Okay, and you're always going to have like the number of subintervals will be one more than the number of exclusions. Here we have 1 exclusion, 2 subintervals. Here we have 2 exclusions and 3 subintervals. Now, also another item to focus upon, okay, we have not only with fractions but also with radicals. And if I have, let's say that f of x is equal to the square root of x minus 7, here we have an even root radical. And for this particular case, right, so you have an even root radical. So x minus 7 cannot be negative. In an even root radical. Okay, now for the square root of x minus 7, you can have the square root of 0 and the square root of a positive. So just in the setup, now for x minus 7, if I were to put this in inequality terms, now it can be greater than or equal to 0. And so we have for isolating x, we have upon adding 7 to both sides, now we're going to have the defining inequality where upon x is greater than or equal to 7. So just kind of a quick sketch in terms of taking the graphing solution of the domain. So you have x is greater than or equal to 7, equal signals that 7 is included. So instead of a hole, we're going to have a closed point. The rest of the values have to be greater than. So we'll have a ray that's going to go out to the right. And approaching infinity. And so we're going to have for the domain, okay, again, so we're starting from and including 7. So 7 is going to be, instead of a parenthesis, we'll have a bracket. And again, we have approaching infinity, which is boundless. So this portion here is going to represent the interval notation solution for the domain. Now, if we have, let's say, a function and we'll say we have f of x is equal to the square root of 8 minus 2x. Again, because we have a radical that is an even root. Again, 8 minus 2x cannot be negative. Okay, but just like x minus 7, it can be 0 and it can be positive. So we can set up that 8 minus 2x is greater than or equal to 0. And if I look at isolating the variable term, so I can proceed by taking 8 away from both sides. So right now we have negative 2x is greater than or equal to negative 8. And again, I want to isolate x by division. Okay, so if I divide, okay, we're going to have dividing by negative 2 in this case. And once again, if I multiply or divide by a negative, I'm going to change the direction of the inequality. It's not adding or subtracting, but with multiplying or dividing by a negative, the direction of the inequality changes, in this case from greater than or equal to less than or equal to. And we have with the inequality solution, we have that x is less than or equal to 4. So in the case of the interval solution, okay, just from a graphing perspective, the equal sign, once again, signals that 4 is included. And the rest of the values, okay, we have with the ray that's going to go continuously to the left. Again, the lower limit we have approaching negative infinity. And so we have with the domain, okay, so we're going from negative infinity. And we have and approaching and including the value of 4. And just like the 7 earlier, because 7 was included, we're going to have 4 likewise included, and it's the enclosure in the interval notation will consist of a bracket around the value. Okay. And then we have just another scenario. So we looked at where there were domains outside of all real numbers, okay, those arising from fractions and even root radicals. Let's say if you have a synthesis of both, and we'll say that we have f of x is equal to, let's say we have 2x plus 5 all over the square root of x plus 10. Okay, so we have a simultaneous appearance of a radical as well as a fraction. Now, the restrictions, okay, will come from focusing upon what we have concerning x plus 10. Well, there's a twofold situation. First of all, x plus 10 is inside an even root radical. So again, x plus 10 cannot be negative. And because x plus 10 is not only inside an even root radical, but it is also situated in the denominator of the fraction. You also have that x plus 10 cannot be 0. So x plus 10 can't be negative, can't be 0. So just looking at filtering things through, turns out that in terms of any category, x plus 10 can belong. Can't be 0, can't be negative. X plus 10 must be positive. So in terms of an inequality setup, if x plus 10 is positive, we have that x plus 10 is greater than, not greater than or equal to, only greater than 0. And if I take 10 away from both sides, it's going to turn out that to keep this function f of x real, that x must be greater than negative 10. So you have just like a graphing display here. So for x greater than negative 10, so on negative 10 we're back to a whole on negative 10, and then you have greater than, so we're going to have a whole from the whole. We're going to have a ray that is going to go out to the right. Again, going out to the right means an increase from the negative to the positive realms within the real number system, and we have approaching infinity. And so we have with the domain, okay, so we have going past negative 10, so that's going to be in the parenthesis, and we have going out to infinity, and that will be the interval solution for the domain. All right, and now we're going to be looking into linear equations into variables, and just kind of bedrock to what we are going to be looking at with linear equations. Okay, for linear equations in two variables. Okay, first of all, we're gonna be looking into slope. Like the slope of a line. Okay, and now for the slope of a line, that's going to run through 2 points. And we'll just label these 2 points in the general case where we have x01, y01, and x02, y02. It's going to be, and we have the variable that's going to represent slope. This is the most common one I do see. This would be the letter M, and you're looking at y02 minus y01 all over x02 minus x01. Okay, some books might have it as y01 minus y02 over x01 minus x02. But regardless of which combination you use, in other words, whatever leading subscripted value you have, you want it to be the same at both top and bottom, because you don't want any crisscrossing like y2 minus y1 over x1 minus x2. So you want the second minus first over the second minus the first, or vice versa. So for the slope, you're looking at the amount of vertical change with respect to horizontal change. And just for this, okay, for the slope to be defined, okay, you cannot have the denominator to be equal to 0. So x01 and x02 cannot be the same. But let me do mention, okay, if you do have a run-in where you had the same x values for, or the same values for x01 and x02, here's the domino effect that's going to be created. If x01 and x02 are the same, then x02 minus x01 is equal to 0. Then you have the slope m would be undefined because you have a 0 denominator. And what would happen here, you would still have a line. And if you have only the y value changing, but the x value just remains fixed, the only motion there is just going to be either up or down. So that means that the line would be vertical. Okay, so anytime you have an undefined slope, you're going to have a vertical line. So the only change to be occurring will be vertical change. But for a defined slope, you should have horizontal change to come about. Now, and where we have, in the case of a defined slope, now let's say that if you have so you're looking for the slope of a line. That's going to run through, let's say we have -1, -4. And 3, 6. Okay, so you're going to have here, so with the ordered pairs, so you have -1, -4. Okay, so I have -1, -4, and 3, 6. Here we go. Okay, so you got 3, 6. Okay, now in terms of what we have here, so -1, -4, and 3, 6. If I determine the slope through the formula, again, I had the slope equal to y of 2 minus y of 1 all over x of 2 minus x of 1. So in terms of just going ahead and labeling, okay, so remember all ordered pairs are the form xy. So if I let -1, -4 be the first set of x and y values, and 3, 6 be the second set. Now it could be the other way around. Have 3, 6 as the first set, -1, -4 as the second. You will still have the same slope. We're just taking what we have now. So for y of 2 minus y of 1, y of 2 we have at 6 minus y of 1, so we have subtraction of a negative. X of 2 minus x of 1, x of 2 we have at 3 minus x of 1, so x of 1 we have at -1. So we have 6 plus 4 over 3 plus 1. 6 plus 4 is 10. 3 plus 1 is 4. So in the big picture, the change in y we have 10 units. Change in x you have 4 units. And if I were to break this down incrementally, now the slope is going to be at 5 halves. So just looking at it from an incremental standpoint, like 5 halves, this be like you have the vertical to horizontal change. So like if I read in order from left to right, the 5 is in reference to moving up 5 units, and the 2 will be in reference to moving out to the right 2 units. And let's say that we have with the graph points -1, -4, and 3, 6. Say if I move from here up 5 units, So I move up 5 units, and then I shift on over 2 units. And we have like an in-between point. So if I go from -4, so up 5 units, I'm at y is equal to 1. And if I go out 2 units, I'm going from x equals -1 to x is equal to 1. So I have like an ordered pair at 1, 1. And if I went up, let's say another 5 units, and then shifted over 2 units, think of it kind of like a staircase. You have like up 5, right 2, up 5, right 2, and your next point would be 3, 6. Okay, so yeah, like going from -1, -4 to 1, 1 to 3, 6, and to stay on this line, I would have a cycle like going up 5 and to the right 2 units. So this is just again, so this is with the slope formula. So you have the slope at 5 halves, and again, just with the drawing. Okay, this is just like a triangular representation: up 5, right 2, up 5, right 2, where you still have the points -1, -4, and 3, 6 connected by this straight line. And we'll be looking at various types of linear equation formats, using in many cases slope as a foundation. Again, some reminders. This evening, okay, will be the deadline for submitting the first test, and also in ALEKS, okay, I adjusted the due date for section 1.3 to Saturday night at 11:59 p.m. Section 1.5 will be due Monday night next week at 11:59 p.m. And I do have simulations for these particular sections in the weekly notes tab, and items you can go ahead and be looking into. We have page 147, numbers 44, 47, 56, 100 parts A through C, and also 104 part C. And for page 162, you can go ahead and be looking into numbers 27, 30, 39, 42, 52, 62, followed by the number 80.